So, on the lab, here was the basic idea. Was that you had an incline, you had the magnet, okay? And then basically what was happening, and this is the whole point of this lab, about why this is always a braking force. It's never going to create a force that's going to make this thing speed up. And so this is actually what they use on some roller coasters to slow it down, because of the fact that it will never act as a force that will speed it up. So here's the short version, and this is what we talked about yesterday. So let's say that you just make it simple, and you have like one wire loop on a cart that's moving in. So you have two things that are going to happen. So what's going to happen is that, how did my X's disappear? So as this is going through here, it's going to, so here's your magnetic region. There's nothing here. This cart is going in this direction. So as it senses that increase in X's, what's it going to do?
Create more O's.
It's going to create O's, right? So the question being is that which direction does the current have to flow to create O's inside of the O? So counterclockwise?
Counterclockwise.
Okay. So the current is going to be created in a counterclockwise direction. Now you use the right-hand rule again. Then you go, okay, well the current in this section of the wire is going down. This magnetic field that it's moving into is going into the page. Your fingers point to the right. You then force this thing to slow down because it's creating that force that's acting on that wire. Now, when you do this, and I promise you on Monday, if you hand in the test and you have not done a question like this, you have done something wrong. If you look at F equals Bill, it's only this length of the wire that's at like in a cross section to it. This length here doesn't make any difference because it's parallel with it. Okay, it's only that which is going to be entering that leading edge of that wire. Okay. So when you get to the that last part, so make sure that there's a couple of things that you have on there. Indicate if it's making more X's or dots. On the vertical line, they would indicate the direction of the current and then show the direction of the force. So you should have kind of three things there. Are you making more X's or are you making more dots? Which direction is the current going on that line? Is it going up or is it going down? And then what's the direction of the force? Either left or right.
The original one has O's, doesn't it? Has O's coming out.
On the
this one.
lab itself?
Yeah.
That I can't tell you.
Why not? Because then what if we get it wrong?
And Franklin had
50-50
I feel
shot.
like it's O's.
Benjamin.
Lily?
On number 9, right above that, it says that the length of the plate in the actual magnetic field is 5 centimeters. Do you want us to just use that value, or since there's 2 plates, would that be 10 centimeters?
No, it's just one. Just like we're just modeling it as one loop going into that thing. Yes, technically there is one on both sides, but we're just going to look at what's going to happen just on that one.
I can't find my lab. Do you have another paper? I've looked in my backpack.
Does our free body diagram need to be to scale?
So,
No, because it says sketch it.
Okay, good. Because the forces are very different vectors, but whatever.
I know, that's why I said just sketch it.
can we go check?
Okay. Are we good? Anything else on the lab? Going once, going twice, sold. Okay, get that handed in. Dropping into the ring, and then there was a wire with a cart going down below. So let's start with that one.
Oh my god, this is
Yeah, this one.
Oh wow, 3 pages. I guess I should end this.
All right. So obviously, if you're going to figure out the first one, what do you have to know?
Probably need to know
Nope.
north to south.
Yeah, you have to know which direction the magnetic field is traveling. Okay? If you don't know that, you are screwed right from the get-go. Right? You cannot answer this question. So, here's the question. The magnetic field lines originate in the north, go to the south, or start at the south and go to the north.
North to south.
So these magnetic field lines coming around here like this.
Don't
Right.
question this, bro. Don't question this. Don't make me change it again.
So, here's the story.
Okay?
If you're in the plane of the loop, okay? So,
Let's see.
here's the North Pole, right? South Pole. So if you just hold this right here. So in the plane of this loop, are there X's or O's?
O's.
O's. Why?
Because north to south. That's
Coming up towards this, right? So as this falls, what are you increasing the intensity of?
O's.
O's.
More,
So to compensate,
more X's.
you got to make more X's. Okay? So because of the fact that there's O's, you have to make X's. So in the plane of that, how are you going to make X's? Which direction is it going to go?
clockwise.
So the first current is going to go clockwise. Now, the second one, after it falls through, now you have the North Pole. So the North Pole, right,
Out.
is
So those are O's.
they're coming out. So if you just hold this right here,
So is it
if you
still
just hold it
clockwise?
right there, don't move it. If you just hold it down below it. In the plane of that ring, what do you have?
O's.
X's or O's?
O's.
X's.
I
Oh.
thought O's. It's, and the north is coming up.
Okay, because this is the
Which has to
North
look
Pole,
at it
right?
Yeah.
both times. Or if it's-
So those magnetic field lines are pointing up like this.
Yeah.
Doesn't matter.
Those are O's.
So in the plane
You
of
can't
this
switch ways.
ring, they're coming out.
Yeah.
So you have O's, right? So as it falls away, what are you doing?
Less
Less
O's.
O's.
You have less O's.
And you
So to
increase
compensate,
O's.
you need to make
More X's.
more O's. Right?
Not X's.
So if you decrease O's, you make O's. If you decrease X's, you make,
X's.
but if you increase X's,
You make more O's.
you increase O's. If you increase O's, you make,
More X's.
so whatever it's increasing, you make the opposite of. But whatever's decreasing, you make the same of. So that leads you to which answer?
A.
Fantastic.
Let's
A.
go.
Let's go.
Let's go.
Let's go. Okay. He has it's a short little video, but this guy's dog is watching like soccer. Have you seen this? And the dog's like, it's just absolutely infatuated. They're watching television. And there's a score, you know, the goal, and the announcer goes, "Go!" And the dog is like so excited, it just like falls over. It's a cute video. Not that I like watching animal videos, but that was really cool. Okay, so you have a loop of wire going this direction. It's going to hit that magnetic field.
It is.
So this is just like the lab that we just did yesterday.
Yep.
So what's going to happen? You have to
Increase
use the
O's.
right hand rule twice.
B.
So Sam says B. Why, Sam?
Because it goes into the X's, so there's gonna be more O's. It's gonna make more O's.
So as this hits, right?
Yeah. It's gotta make more O's.
Got to make more O's.
inside, and then you get.
So you're using the right hand rule, so you're going to try and make more O's. So which direction is it going to go to make O's?
this way.
Up
Counterclockwise.
or down?
Up.
Counterclockwise up.
Up?
Yeah.
Because you want to make,
Yeah. Yeah. Counterclockwise.
Isn't that
That's clockwise.
That's clockwise?
Yep.
No, it's not. That's counterclockwise.
Look, it's going up like this and coming.
Hold on.
The clock.
Sam,
No, it goes like this.
if I send it up like this,
Yeah.
Oh,
And
we
wrap
want it
that
in the
around.
plane? I thought we were talking about the cart.
we are.
Yeah.
We're
So if you
talking
wanna
about the
make-
one on the bottom of the page.
Of wire.
Okay?
Yeah.
So here's my question. As this leading wire goes through,
Yeah.
you have X's which are going into the page, right?
Yeah.
Okay? So you need to make O's.
You do.
In the cart though, right?
Yes, on this section of the wire, right? Okay? So in this section of the wire,
Those go out.
you need to make O's,
Those go out.
which means you're gonna do which way? Are you gonna go up? Are you gonna go counterclockwise? Or are you gonna go clockwise?
Counterclockwise.
Counterclockwise.
Because you want this going up like this,
Yeah.
so that that's coming out like this. So on this leading section, let me change that.
B or D?
It's B because the glider slows down.
Yeah.
So on this section of the wire, you need to make O's coming out. So that's gonna send this thing around that way. So, but then you're gonna use the right-hand rule a second time.
And force.
Current's coming up, the magnetic field is going,
And.
your braking force is going to act in the opposite direction, which leads you to the answer of B. There you go. Jackson.
Never speed it up.
No, it will never, ever, 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 ever.
Not even
Ever.
if it's O's?
No.
Really?
Because then it's just the reverse process.
It is, isn't it?
Everything's just gonna get flipped. Yeah. It will never make it speed up. Okay,
Interesting.
now,
Gosh.
on the next one, same idea, right?
Ugh.
So, on the diagram below, indicate the direction of the induced current. So with this one, so here's the cart. What's the direction of the induced current?
In.
Up.
Oh, counterclockwise.
Oh, I'm sorry. I thought you meant the field. No, sorry.
On the
I thought
figure
X's.
below,
I
indicate the
got
direction.
Counter. It's the same as the last.
It's the same as
Aye.
the last
Trying to
one.
make O's.
Exact same thing.
Yeah.
Counterclockwise?
Yeah.
Because
Okay.
field
Go with that.
increases in
Yeah.
carts.
So, then, and when it says justify your answer, for those of you that are actually taking the test, whether mine or that one, here's what you cannot say because of the right-hand rule.
Can you say you need to increase O's?
That I can live with. Okay?
Can the AP test live with that?
Yeah.
No.
Why does it matter
What if I
to me?
said
Why? It's a valid reason.
No. Hold on, which answer?
The O's.
Just by the
The
right-hand
O's.
rule, or
The
were you talking about
O's.
Vitor's answer?
The O's.
Oh, I thought you were talking about, no, that's what I'm saying, on the AP, you just can't say go by the right-hand rule either. You need to say, it's gonna go in that direction because of the right-hand rule, indicates that you need to make more O's, okay?
Can I say Mother Nature must?
Yeah, what if I said
On the AP test, it's like-
Can I say because field
Yeah.
increases in cart and Mother
They're going,
Nature
who are these kids from Maine?
must
deal with
create
Mother
more
Nature?
O's?
Okay,
I'll take your motion.
now, so what do you have
Fourth law, right rule.
on the magnitude of the induced current in the rectangular loop of the wire?
Wait, we're supposed
We
to do
didn't
this
do
whole
that.
page?
Yes,
That is funny.
I did.
I was like, wow, this is so
Don't
like
give her participation points for today.
magnitude of the induced. I feel like it's the B squared
Stop the
L
camera
squared V
again. I'll
squared.
give you the, stop the camera. So,
Yes.
you want to find a current, right? So if you look at what they've got for you, you've got Ver, right?
Ouch.
So
Yeah.
if you look at what you have up above in terms of that information, they tell you that the wire has a resistance of 4 ohms. Okay?
Yeah.
So if you Ver it up, V over R, you know your resistance. What you don't know is the voltage. So what can you do to calculate the voltage?
Believe.
You can believe.
I believe.
That we just
Is that on the equation sheet? Or should I have to memorize that?
It's there. But it's shown as that fancy E,
Oh, that's fine.
or is electromotive force, which means the
I'll
same
do
thing.
that.
The sheet?
Now,
Oh, I
Here's
see.
the question. You have a length here, not angular momentum.
Right.
You have a length.
Point one.
Do you use the 0.2 meters
Heck, no.
or do you use the 0.1 meters?
0.1.
Wait,
They're
how is,
parallel.
so is that
What?
equation?
Oh, yeah,
different from the one on the
ridiculous.
bubble sheet?
I bet you.
What, Louis?
Is that equation different from the one on the bubble sheet?
What?
No, same one.
Oh, I'm sorry, okay, I see.
I just substituted for voltage, which is the same thing as that fancy E.
I got you.
I just put in the belief.
And then a little bit is, so force magnetism is mil, right?
Is what?
Is mil,
Yeah,
Yeah.
EIL?
yeah. Bill.
Yeah.
Sine
I
theta.
thought you said little. And I'm like, what?
Bill.
Okay. So anyways, your current
It's Billy.
should be 0.15 amps.
Might wanna start the camera.
I'll do.
It
It started.
Oh, it is, okay.
Now, how are you going to get the
0.15?
force
My bad.
on part 2?
Bill.
Bill,
Bill.
build it up.
Let's get you Bill.
Which should get you 0.03. Now, when you get to C at a later time, the current and loop are completely inside the magnetic field. You determine the magnitude of the net force on the loop at that time, justify your answer. What's it going to be?
Yeah.
0. Why?
Because you have
No
two that are
change
going,
in
yeah, or they'll cancel out.
Is anything, well, number one, is anything changing if it's completely inside the loop?
No,
No. What's the only time you induce a current?
It's
if there's an
moving
imbalance.
or change.
If there's a changing magnetic flux.
Ah.
So if that whole thing is, so here's my magnetic field, and that whole thing is inside of it, then there's not going to induce a current at all. Like there is no current. There isn't, oh, one's positive and one's negative in terms of forces. There's nothing, because there's nothing changing. Okay? All right. Now, next one. Try, this is one big problem that starts on one side and goes on to the other.
All near 4.
Which one?
All near 4.
2011, number 5.
2011?
2011, number 5.
I'm going to the right.
Go. Okay. So this whole problem has great historical significance because this is how we actually figured out how the universe worked in terms of finding these subatomic particles.
We know how the universe works.
No, we don't.
Well,
That's a
actually
lie.
we don't.
That's such a lie.
Okay.
My physics teacher, my physics teacher lied to me.
Yeah. Gravity, whatever. Okay. So you got this action going on, right? Now, here's the whole key to this. You have two things going on. Okay? You have two things. You have a plate and you have a magnetic field. Okay? So here's the whole thing that I want you to see. If you choose, let's say you just have one of them. Okay, let's just play the what if game.
What?
What if you only have that positive charge right there? I hate this thing.
Are you using different software now?
Yes.
Yeah.
Well, yeah, but it was working and now it quit again.
You just have a bad deal.
No, this is a new
I know,
loaner
with
laptop.
your writing stuff.
So it was working like a champ.
It's like this class.
Now it started again.
This class,
Okay.
it does not like you.
No, it hates it all the time. So here's the story. Let's just say it's
Velocity.
I was so confused.
He dropped
on what
his
he was
eraser.
doing.
He dropped it.
Force.
Yeah, he dropped it.
okay. So let's say that you're sending that positive charge in between. Don't worry about the magnetic field. Do not worry about the magnetic field.
Don't worry about the magnetic.
Don't worry about it. You should a positive charge in between this positively charged plate and that negatively charged plate. What's it going to do?
Go
Curve
towards the
upwards.
negative charge.
Go towards the top or go towards the bottom.
Top,
It's gonna go towards the top. Why?
because it's a
Because
positive
it's a
charge.
positive charge.
So it's gonna be repulsed by the positive,
They also tell you that the E
Attracted
goes
by
up.
the-
attracted to the negative.
Yeah.
Now, let's say they didn't, because I won't be this nice. So
Oh.
what's the direction of the electric field?
Up,
Up.
maybe.
Because that's the
Put a
direction
positive
Yep.
test charge.
it's gonna take, right? Cool with that?
Valid.
Got it.
Yes.
Very much so.
How could you find the magnetic field? How could you find the force acting on that particle?
Egg.
Thank you.
Egg.
But they don't tell you E.
We're just
Oh,
deriving
we're just
an equation.
deriving the equation. I don't even know what a deriving is, but
Okay?
It's like we have to make an equation, right?
True?
Or something.
like with substitution.
That's the force in there.
That's what
Now,
I did. He said nope.
let's just now leave out the electric field.
Okay.
Let's just focus on the magnetic field. You have, now you're going to use that right hand rule. You have a positive charge. What's the direction from the direction of the magnetic field is?
Out. Out.
Out. So the force is going to be acting down. So the force from the magnetic field is going to drive it downward.
Down.
Oh.
Okay? That's why that magnetic field has to be coming out of the page. Now, how are you going to calculate the force created just from the magnetic field? So the force from the electric field is going to be Fek. That has to equal the force from the magnetic field, not force buoyancy. Okay? And that's going to be what, Vitor?
QVB.
QVB. Now, is that V velocity or is that V voltage?
Velocity.
Velocity.
Use voltage.
Ah. That's what.
What?
Easier than it should
So,
have been.
what do you end up with then? So what's
E
going to
over
cancel
B.
out?
Q. Q.
Charge is going to cancel out.
Divide
E equals.
So you want to solve for V1, so you get
E over B.
E over B.
E over B1.
Oh my god, it's the equation. It's what we needed. What I needed.
Why B1?
Because later on you'll see there's going to be a second magnetic field.
Oh,
Okay? Now,
Perf.
couple of things that are going to be important at this point. Why didn't they give you the mass of the particle?
because
Because you should know it.
Doesn't matter.
Oh.
It would cancel out.
It's not part of the equation. You can't plug the mass into that thing if you try. Would it make any difference if it had had a positive 2 charge?
no, because they cancel out as well.
Yeah, so the value of the charge doesn't matter. Okay?
It's negative, it matters.
Would be, and now it would matter greatly if it was negatively charged. Okay?
Magnetic field.
Yeah, because then it.
Now, but would it though? If you send a negative charge into here, if you put an electron in there, what's it going to do?
Well, you have.
It's gonna fling down.
Just think about the force from the electric field. If you send a negative charge in there,
It'll go down. Downward.
it's going to pull that down,
Uh-huh.
right? Because it's going to be attracted to the positive.
Oh, so you just add.
Now, if you send it into that magnetic field with the left-hand rule,
It'll go up.
It's gonna go up.
guess what? If it was negatively charged, guess what would happen?
It's gonna go up.
Yeah, but you know.
Would it still fly straight through?
Yes.
Maybe.
Now, does the velocity impact how fast that thing is going? Does that change this ratio?
No, it doesn't.
So let's say you have 1,000 meters per second versus 2,000 meters per second.
Don't matter. Well, it does.
Well,
it does.
I mean.
Yeah.
Yeah.
There's
Yeah.
more velocity.
So if
Greater
that velocity
velocity.
gets bigger, what has to happen to this ratio?
Electric
yeah,
field
yeah,
has to
One or both of them has to change at the same rate.
The change.
But here's the whole key though. The forces, if you go back far enough, the idea being is that the force of the magnetic field has to equal the force from the electric field. That's the only way it's going to go straight through. Okay? Cool with that. Now, speaking of which, look at question 2.
It could move in a straight line, or it could
curves toward the top
Down.
because the electric field would be greater
Why is it going down? It's going up.
Up, only.
Magnetic field is greater.
if velocity is greater.
The electric field is EQ.
It moves in a
It's
straight
up.
line.
Why would it move in a straight line? They said that the speed is greater than E over
That
V.
means either E is greater or B is smaller.
Yeah.
And
Yeah, so
Yeah,
that
so
means
then
electric
would
field
make
is-
it
so
go
that
up
means the
more.
electric field is greater, so
Yeah.
force electric is greater than force B.
because B goes down,
That's what I
because that's
said.
the
Wow.
rate of change. So it goes up.
That's what I said.
Oh.
You
Because
said it went
if
down.
velocity
What? You said it was
increases,
down.
Oh, y'all were arguing against me? I was kidding about that.
Oh.
My bad.
then
I said that as like first as a
How is
joke.
it, when
Now
is
it's like
it
it's so
straight?
serious.
You said that.
When is it
When they're
equal?
equal.
When they're
If they're
equal.
Sam, you said you
What did I say?
capper. Capper.
I didn't say bottom, I said.
Okay,
Capper.
now, to settle this, okay? Let's settle this. First off, on this part two,
Go in a straight line.
under A, right?
So you should-
So, what do some of you have as your answer?
Top of the
I'm gonna
page.
say
top of the page.
Top of the page?
Stop.
Yeah,
You say top.
Why?
because
Because
velocity
we think that
increases.
the force electric is greater than the force B.
Yeah.
It is what it is.
If the electric field is greater than the magnetic field, and
Okay,
then your
stop,
mass,
stop.
I feel like we're
Stop.
wrong.
Or are they the same?
Stop.
This is me.
Stop.
But they definitely are the same.
Oh, it's straight line.
Okay,
No, wait.
go back to the beginning.
Good job,
They are the
Gracie.
same.
Go back to the beginning. You have a positively charged particle going through it. Which direction is the electric field going to push it? The electric field is going to push it up, right?
Yeah.
The electric field is going to push it up. True?
What did you get then?
The magnetic field is going to
Push it down.
No, top.
push it down. Now, is the velocity going to impact the strength of the electric field?
No.
No. Is the velocity going to increase the force from the magnetic field?
Yes.
No, it's not.
Yeah, but if it's
Okay, it is.
Yeah.
It's in the.
It's QVB.
Oh,
That's what
let's
goes down.
go.
What do you mean get in?
No way.
So if the velocity gets bigger,
Then FB gets bigger.
oh, then FB gets bigger.
Yes, it
What's
does.
Oh.
ah,
Ah.
That's what
Wow.
I said, bro. That's what I said.
No, it doesn't, Sam. That is so not what you said.
This is
This is a
painful.
bold-faced lie. I'll bet you $1,000 right now. I'll bet you the goatee.
Let's go back in the camera.
Goatee?
The goatee.
That what
Yeah.
calling it now?
this is definitely
Which I
going to be on
cannot
the
wait to
test.
shave off, by the way.
You only got a month.
Over it.
No, if you guys don't hit 100, I have until May 1st. I have 10 days.
We're
QVB.
still at.
I'm about to break some kneecaps.
So
Who
it
hasn't
goes to
done
the
it?
bottom.
Switch up, hold on.
This is the bottom.
Yeah, you who I have spent so much time recording videos and grading great work for, you,
I'm clutching up, don't worry.
okay.
I got you.
Vitor's gonna clutch up.
Vitor needs to use some of that
I will.
pro money he's getting.
Whatever-
Anyway,
whatever my
so it's
friend
going to curve towards the bottom of the page. Okay? Everybody cool with that? All right. Now, on the back side. So, look what happens if you flip this thing over. So let me kind of paint the picture. So you had the negatives, you had the positives, you had the magnetic field. Now, so because this is a radioactive source, the particles coming out of this thing are going to vary greatly in terms of the speed.
Right?
So the whole point being is that only the ones that go straight through have a particular velocity. If they curve up or if they curve down, that means they're going to have different velocities. So basically what this does is that it acts as a selector. So the ones that flow straight through are the ones that you know have a particular velocity equal to the ratio of that electric field to that magnetic field. So if they're curving up, they're going too slow. If they're going curving down, they're going too fast. Okay? So, and how you can figure that out, if you just wanted to find out what was going on, you could just put like a phosphorescent screen there, and this is what they used to do. They would have a phosphorescent screen. And every time a particle, high energy particle would hit it, you would see a flash of light. That's the only way you could see it, because these are like subatomic particles, okay? It isn't like, oh, well, watch them, they're little like bowling balls going across, okay? These are subatomic particles that you could not see. So what you would look for is flashes of light. So you would see other flashes of light up above or down below, and you had to realize, oh, those don't have the exact velocity. They're either too slow or they're too fast. Now, in terms of what you can physically alter, you're not going to change the strength easily of that magnetic field. Okay, here's the magnet. Here's the magnetic field. Boom, this is it. What you can do, and this is what I use with that voltage machine, that power source, I can crank it up and crank it down. I can change the value of the electric field very easily. I can't change the value of the magnetic field because I'm going to have like a permanent magnet. So I can adjust the strength of that electric field to select for a particular velocity coming through there.
So why is that useful?
Hold on.
Sorry.
So what's going to happen in the next stage? So what this is going to do is that you're going to know a particular velocity of these particles coming out. So now they're going to come through here, and then they're going to hit a second magnetic field. This is where this B2 comes into play.
Oh, no, that's where it gets funky.
Okay? Now, here's the story. If you look at what's going to happen, determine an expression for the initial magnetic field, da 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 da. Okay, let's talk about this. So let's just talk big idea. So these are positively charged particles that are coming through that magnetic and electric field. Straight line. Newton's law rules. They leave this. They hit a second only magnetic field, no electric field.
Okay.
They hit a magnetic field that's going into the page.
Into it.
So what's the force that's going to act on these particles?
Magnetic force.
So the particles coming this way, they're positively charged. Magnetic field is
And
into the page.
Force is gonna be up.
So what's going to happen is that this is going to make these particles curve around in a circle.
in a circle?
Because no matter where you go, that force is going to be acting inward.
This is part
Oh.
of
Wait,
it.
inward? Why not up?
Slams some stuff together.
It is up, but then as it changes the path, no matter where,
Ah.
so it's going to initially curve it up, and then it's going to continuously make it go in a circle.
So then what?
Insanity.
So what do you know about the magnetic field, magnetic force? Because this thing is going to be traveling in a circle. The big idea is that you're going to make this thing travel in a circle.
It's centripetal
The
force.
centripetal force has to equal the
MAC.
magnetic force.
Oh.
And if you know the velocity, you know
V
mv squared equals the magnetic force, then you can solve for the mass of the particles. That's the big idea. That's the big picture. Okay?
We have to figure that out here?
Yes, you do.
Wow. What
So-
a question. Who decided to put this on here?
Oh, I love this question. I'm
Really?
so jealous when I saw that. I was like, oh, that's a good question.
So, oh my goodness.
Okay.
Really jealous
In some form.
Some form or another. I promise you. There is going to be, this question is going to be on the test in one form or another. I promise you.
Please don't make me derive an equation.
Oh, you're going to have to.
Define derive.
You have to find derive.
Just like this.
Take the derivative.
Yeah, you don't have to do calculus. Okay. Now, so here's the story. So, this is where you do some substitution. As this particle hits that second magnetic field, how are you going to calculate that second force from that second magnetic field? What are you going to have?
QVB.
QVB. But, is that B going to be 1? Or is that B B1 or B2?
B2.
That's B2. Now, how do we get the velocity?
Divide.
Wait, it's gonna be
V1 equaled,
E over B1.
so instead of this, we're going to put what?
Q E over B.
E over
Oh, because you're not allowed to.
B, but which B?
B1.
B1 times.
It's the one.
Now, can we cancel out the magnetic fields?
We would like to.
No.
You
cannot.
No, you can't cancel out the magnetic fields.
No.
You can't do that.
What's the only way you can cancel out the magnetic
They were the
fields?
They're
same.
equal.
If they were the exact same value. Now, with that said, keep going.
Right?
Keep going
Yeah, work it from there.
here. Are you sure?
Work it.
Yep.
Work it, Sam.
I'm working it. I'm working
Hmm.
Let's say maybe chortle. Describe the changes if green Sam, don't act like you get it.
I do get it.
I'll bet you got it.
Really?
How much?
Like how
I
much?
don't know.
He goes, I didn't get it.
I hope nobody walks in while we're doing that. They'll be like, Mr. Burkamp, we have a word with you. No.
Sam, don't.
Why are you telling
And then Sam's gonna be, I bet they don't fire him. I bet they don't fire him.
He was making a bet. Oh no.
We're just gambling, sir. It's not that serious.
Oh. Okay.
We were just gambling and
No.
then recording the evidence. It's not that
Yeah.
serious.
Charge per mass equal. Oh, get the camera.
What?
Reb.
You don't know that.
It's like pizza.
Yo.
That Ty's trick shots or whatever. Like you said, it was so funny. Okay,
The
guys.
comments were crazy.
Okay, guys. So today we're.
The comments were violating that.
They can't be
Can you give me an
violating my
example?
blood.
They were calling my fish eyes.
I thought they liked that game.
Dude, I derived that so well. What? Because it's force centrifugal. This guy doesn't listen.
I thought it was a G. Your handwriting sucks.
Yes, sir.
Way better than yours.
Yeah,
Yeah.
don't cast stones.
Yeah, live in glass.
You should see my Q1, 2, and 3 because we had our 3-hour AP Lit thing. I read it. Some of the words I couldn't read. It was great. Fries could have a great time.
Theoretically, for the amount that I write, I should be better at it.
Okay, I just told my pencil really weird. And my writing's just screwed from there. So.
Charge to mass ratio.
What? No, you don't.
Just grip it.
That's what it's not I hold my pencil.
Are we allowed to use the radius?
Pencil like this.
Shut up.
You know, people
Swear
do
to
you write like this, Fisher? I feel like
The
you
radius?
do write like that. I knew.
No.
It writes like this.
Dude, a lot of left-handed people write like that because they show
Did
you
you
how to
guys
write
use
right-handed
radius?
when you're a kid,
You did?
and then I never
What's
tried to.
radius?
For V
I
squared
write like how I
power
use
versus
chopsticks.
centripetal acceleration.
Yeah.
Like this.
I really like this.
I don't know how
You write like this.
You write like a normal person.
I don't think you have to use numbers, you just have to use.
No, I know, but can I use
Yeah.
the variable?
Yeah, but that's why it says specifically no any quantity is not previously defined. That is what it's
Oh,
saying.
okay. I think I might got this. Maybe.
Use my pinky to put pressure. I'm wild.
Wait, can I use V?
No, it doesn't.
So you can substitute E for one.
It does.
Oh, it's not like this.
Just look.
Oh, because this is V.
Like this.
But if I
Not like
divide-
what the hell is that?
It's just one V.
Oh yeah.
Oh, wait, I don't divide though. Oh, it is still one V though.
Random word generator.
Connor's just orange.
Connor's the Snapchat.
Swear.
You're exposing me back here.
Exposing me.
Oh, Snapchat, yeah. It's great.
Connor, when are you gonna take the circuits test?
Huh?
When are you gonna take the circuits test?
You haven't
Monday.
taken this.
I can't take it today. Because I have work at 3:30.
You haven't taken the circuits test. No. Dude, you're so screwed. We haven't done that in like 2 weeks.
I'm taking it Monday, taking the magnetism test Tuesday.
You say that like.
Imagine, is that the first time you heard of it?
Yeah. I made that plan.
Like,
I made it at lunch.
He's manifesting right now. Just leave him alone. Leave him be.
Give myself
I'm
a
not
weekend
taking
to
the, I'm not
study.
taking the test Monday.
That's crazy.
A weekend to study? I'm
Yeah.
not.
You're not gonna study though?
You're not
No, I
gonna study.
probably am, especially for this game.
This test
Not for
will
the
hurt.
circuit
This
test, though.
test will hurt you.
Oh my
Why
I'm
do you
telling
say
you
that,
right
man?
now.
I got a 93 in here right now, bro.
How much? Is it really weighted?
Are you gonna let us do
Is it
corrections?
a lot of points?
That's on
93.
Well, if it's at her office, then
I'm
yeah,
gonna
probably.
need correction.
Mr. Birdcap,
What?
I'll tell you this right now.
Please just let me have an 89.
Whatever my score is on the
here.
test is what I'm
Reds.
donating to the solar fund.
Wait, like.
Out of 100 or out of 1,000?
Out of 100.
Oh, I thought you say, well, I'll make this thing.
Right there.
I'll make this out of
Wait,
1,000, Sam.
No?
Wait, point? Like.
Like percentage.
Percentage.
Okay, a percentage. That's what
It's
you're
like
donating.
It's like a 22.25. I'll donate $22.25.
If
Why was
you
it
get a
20?
22% on this test, you tried to fail.
Anything higher than 25 is not going to be applicable to this deal.
Whoa, 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 whoa.
Hey,
You
make a
can't,
bet with him. Gamble with him.
no, you can't start down this road
No, you can say, okay.
and then go, oh, but there's an upper limit of 25.
Okay,
Let's
there's
put the
a limit.
over.
There's a limit of 100, but then we're gonna dice roll afterwards. And
I would-
that's on the
and
dice
put it
roll.
over
And
under on
then
his
we'll see
grade.
whatever it comes
No,
out.
you're pulling a Connor, man.
See, but then we'll do a double.
See, you're changing this, and you're telling me about this whole thing as it goes. This is the first I've heard of this. Okay.
Set an over under.
Yeah.
If he hits the over, then
What's
Oh, that's
he doesn't have
Whoa.
Oh, we should do an over under on my grade and then. Oh,
You know what we could do? We take
okay.
his
Well,
grade,
there's a lot of
he's
things
gonna
we
grade
can do.
hard.
we take his grade, we roll a dice, and that's what we divide it by. So if he gets a 1, his grade's divided by 1, that's what
We're
he
going
gets.
to say under.
So if he gets a 6, he divides like $15, and gets like a 95.
yeah, if you get
That's a good good. That's
Or that's what we multiply it by to get his contribution.
No, he gets 100%.
Or every.
He gets
point- every point
100%,
right
we
is
roll the
5 cents.
dice, we get
See,
a
I like-
6.
I like
$600.
I like Vitor's over under idea.
Yeah, over under.
Shane doesn't want to risk
I'm
it.
just going to grade.
Then are we gonna bet the over under on pop on the time?
Oh, we can do time.
Oh,
time is
time.
probably.
Whoa.
Time's tough.
Hasn't Pop been getting pretty good with it though?
No.
How many?
Okay, all right.
Pretty solid.
Morella, start that up.
It's been going
Oh, really?
for
Hi, Pop.
25 minutes straight, actually.
High five.
Okay,
What's up, man?
Oh, but
It's
so,
gonna be like skipping through like.
okay. I wish you wouldn't do that, because then it takes so long for me to upload and process
Hey,
this.
it was not, but it's been going on since we've been like explaining about this. It's not like we've been talking for 25 minutes straight.
Okay.
There's been important
Anyway.
information.
Doesn't mean it filters it out.
So
I
here's the
was like a
story.
good 5 minutes.
So here's the magnetic field. This positively charged particle is going to come into it. So what's it initially going to feel?
Magenta.
An upward force. Now,
Yeah. Doesn't it decrease the force?
hold on. Okay? So that force, FB, is going to be QVB, right? True? So is the charge going to change?
No.
No. Is the velocity going to change?
No.
No. Is the magnetic field going to change?
Yes.
No.
From 1 to 2?
But no, this is when it's in the second
Oh
region.
no, not if it's going on a circle.
So if everything stays the same, what's going to happen to the value of that force?
It's gonna stay the same.
The value is going to stay the same. But the direction will change, but it will always be pointing inward, which is going to create a centripetal force.
Wait, I thought we said FB2 equals QEB2 over B1.
We do. We did.
So don't you have to divide by a B? So wouldn't that decrease?
What's the last one, actually?
But B1 is
We're talking about just B2, yeah.
You know everything about
This is when it's in B2.
when
Takes off your VR headset.
So, what do you have as your answer for D?
Circular.
Going clockwise or counterclockwise?
Counterclockwise.
Counterclockwise.
So you don't want.
LOL.
Now, when you get to E,
E.
so here's the idea. The centripetal force is equal to your magnetic force, right?
Yeah.
So, your centripetal force is going to be mv squared
Over R.
over r. True? Okay? And that's going to equal the force from the magnet, which we said was
QE1.
EQ B1 over.
B2.
B2.
So all I did was just take that and rearrange that a little bit. It's actually B2 over B1. My bad. B2 over B1. My
I
bad.
was so lost there for a second.
B2 over B1. So what do you want to do?
Well, let's cancel out the E over B1.
Why?
That's velocity, so you can just delete it.
Well, let's not.
Now,
What do
let's
you
keep
mean no?
that.
What?
Let's just,
How?
like,
Hold on, hold on, hold on, hold on, hold
To be
on.
honest, let's just put Q over M.
V square V equals E over B, so then you can divide the V, but you make that V in your mind. So then it's actually only one V when you divide it over, and then you'll just keep it as E over B.
Now, if you want
know
to
what I
do
mean?
that,
But then it's
Okay.
V2, and then V squared is that have to be B1?
Then it's still QVV though, right?
so if you substitute, it's a valid point. If you put this as QVB, right? That's a B. So that's B2. Could you cancel out one of the V's?
Good.
Yeah,
Because they're the same.
Because they're the same.
Yeah.
Okay? So that leaves us MV over R equals,
B2Q.
now which B is that?
Two.
B2.
QB2, right?
And then you just
Now,
solve for M over Q. I mean,
so
Q
if
over
you
M.
put Q over, so if you get Q over M by itself, right?
And then you resubstitute the E over B1.
So what do you get?
E over B1 times B2 times R. And you have to be like, oh, by the way, R equals radius.
Fantastic. That's it.
Wow.
Oh, really?
That's it.
What if I had B1?
Wait, so that's
What
flux?
if I had B1 B squared over R E B2?
Well, here's the deal. So
No, the,
on here, but it says up there that you want this express the algebraic answers in terms of E, B1, B2, and Q.
At least
Oh.
this isn't on a Thursday.
Oops.
For real.
what is Coulomb per meter equal? Is that volt?
Coulombs per meter?
Yeah.
Really, that's coulombs per kilogram, because that's
Oh, that's
mass.
math. Okay. My bad.
Now, here's the story. Look at this quantitatively. So if you look at like the value of the mass of an electron to the mass of a proton, okay, these are extremely small values, okay, extremely small. We can't take an electron, put it on a scale and go, oh, there's the mass of an electron. So this is what we did to figure out the actual values. So we could measure the strength of an electric field, we could measure the strength of the magnetic fields. So what we would do is we'd measure the radius. So we would shoot these particles through, and then we would basically see where these flashes of light are occurring. Now, an interesting thing happens. Number one, if they go up like this, what do you know about the charge of the particles?
Positive.
Positively charged, right?
Yeah.
Now, what if we put a different radioactive source and we see particles, then we see flashes of light down there?
Negative.
Oh, then they have negatively charged particles, right? Now, what do you know about mass protons and electrons?
Different.
They're different.
They're not the same.
$20 says we're different. $20 says which one has more mass?
Protons.
Protons. So, what do you know about electrons and protons?
They have opposite
terms of
charges.
charge.
Opposite.
But the numeric value of the charge
Equal.
They're the
is the
same,
same.
not different.
Not different.
1.6 out of times.
So here's the story. If they both have the same charge,
1.6 times.
as the mass gets bigger, what happens to this numeric value?
Decrease.
This
that's a good
becomes
question.
smaller, right?
Way smaller.
Way smaller.
Wait, can you repeat that?
Okay, if the mass gets bigger, like if you could shift from an electron to a proton,
Yeah.
same charge,
Oh, the ratio gets
ratio becomes smaller
smaller, yes.
because you're divided by a much bigger number.
Yeah.
So this number is going to become smaller.
Yeah.
So then you're not going to change
E field.
the E field. You're not going to change the magnetic field. God. So if this number is getting smaller, then because you had a bigger mass, what
Does
has
the
to happen
radius
to the
have to-
radius?
Oh, it has to increase.
Oh, it has to increase. So a
Yeah.
proton is going to curve up with a big radius. An electron is going to curve
Down the small radius.
small radius.
Tiny radius.
Now, if you can figure out what the charge was done, if you can figure out the charge, then what can you figure out?
Magnetic field.
Well, more importantly, if you know the charge and you know the numeric value, then you can solve for the mass. And that's how we figured out the mass of electrons and protons.
No shot.
Here's another hurt time.
Aspen?
Why are masses of like subatomic particles measured in like electron volts?
Because it's an easier thing than basically writing out the times 10 to the negative 31st. We'll deal with that in the next unit. Because that's how you're going to measure mass and energy in electron volts. Louis?
Imagine this is on your test.
How are some magnets
that.
stronger than other magnets?
It has to do with the strength of what's called the magnetic domains that are within it. Basically, it's a magnet consists of, if you look on an atomic level, there's a whole string of like magnets, tiny magnets that are all lined up. Okay? So basically, on a really, really strong magnet, you have a whole bunch of really, really, really tiny, strong individual domains. Typically, they're neodymium magnets. Okay? So basically, those can have very, 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 very strong individual magnets within it. And that's the difference. It's the strength of the tiny magnets that make up the collective whole of the magnet. So that's the short.
One tiny magnet equals
Okay.
one magnet.
Virtual always is a bigger green, buddy.
Let me see which one. So this question with the loop
Bigger car.
and the wire.
The wire?
Wire.
The wire.
The wire. So just let me kind of paint the big picture on this one. I'll send you the answer keys to these last ones. I just want to paint the big picture.
No.
So
Want the answer key?
with this one, the whole key to this one is that
Number 3.
on this question number 3, this question comes down to one concept, and that this whole thing is happening, and it has a constant speed of 1.8 meters per second. So since it has a constant speed, what do you know about the sum of the forces?
They're equal.
They're going to be equal, right? So what's going to happen is that you're going to have a force to pull it. You're going to have a force from a magnet. Now, eventually what's going to happen is that you'll also see that there's going to be some frictional force involved as well. Okay?
What?
Yeah, so it makes sense once you get into the problem. So what do you know about the direction of the frictional force?
It's always
Opposite.
opposite.
Always in the opposite direction of motion. Okay? So keep that in mind. Okay? Your force is always going to be in the opposite direction of motion. Okay. I will send you out the answer keys to those last two problems. If you have not handed me that magnetic lab, I need it. You might work on flexibility over the weekend with the right-hand rule. You're going to be using that a lot come Monday. We'll do some warm-up exercises on Monday before I give you the test. I don't want you to strain a muscle.
Thank goodness.
Gotta pull a handy, Mr. Bergkamp.
Huh?